All right, good evening. This is April the 9th. This is Math 2414. It's Calculus 2. A couple of quick announcements. First of all, homework is due on April the 15th, but I do want to let everybody know that I'm going to do homework a little bit differently this week. I will be sending you a document with somewhere around 15 or 20, or I'll say 10 to 20 at this point, 10 to 20 series, and I'm going to ask you to tell me or show me how those converge or diverge. And what I will do is later in the week, I will tell you which of those problems I'm going to pick up specifically. That document will be sent out probably tomorrow. So document sent out tomorrow. And that document will have those series on it. And then I will pick some of those problems and ask you to turn those in later in the week. Several reasons I'm doing this, but in particular, I want you to have a good group of problems that you can use as review for exam 3. And that's one thing that those series will do, is they'll give you a good group of problems to review. And then also it'll give me a chance to pick up a few of them and see if you're doing okay with series. As I mentioned in lecture last Wednesday, this is really, really different than what we've been doing in the past. I'm asking you to justify conclusions and writing things out, so you have to be very careful about that. And I'm going to be kind of picky about what you write out for series and whether a particular series of constants converges or not. So this will give you a good practice for that. After April the 15th, I will then post the solutions to that document, and I'll upload all of the worked out problems completely, however many of those are, and that'll be a good solid review of the primary test that we're looking at for convergence of a series. Okay, so I wanted to point that out at the beginning of lecture today. Live lecture on Wednesday. One other thing to mention to you is I will not be doing that, posting that lecture in the evening at 7 p.m. like usual. On Wednesday, I'll be lecturing at about 1:30 and go about 1:30 to 3, somewhere in there on Wednesday afternoon. So I just wanted to point that out also. So live lecture on Wednesday is going to be 1:30 to 3 p.m. Exam 3. The actual review for exam 3 will be posted by Thursday of this week. I'm hoping a day or two earlier than that, but for sure by Thursday. The window for taking exam 3 opens April the 19th and runs through the 24th. Office hours. Remember that I have online office hours Tuesday, Wednesday, and Thursday from 11 to noon, and then Sunday and Tuesday from 8:30 to 9:30 p.m. So don't hesitate to come by anytime during those online office hours. I will be happy to answer any questions that you have. And if you're working on sequences and series in Chapter 5 and then in Chapter 6, I think unless you've covered this before, you're going to have some questions. And so don't hesitate to come by so we can go over some things. I'll be happy to help you out. Also remember that I do occasionally make office hours by appointment, and so online office hours by appointment I can also do. Just let me know that you want to try to do that, and we'll see if we can work out a time that's mutually agreeable where we can talk about some problems outside of my regular online office hours. On campus hours, I will be on campus April 18th and 19th. So make sure that you are aware of that. Put that on your calendar. Don't hesitate to come by my office in Winship 115, and I will be happy to help you out if you have some questions. All right, today I'm going to say convergence of series continued. We're talking about series and when a series converges. Remember, when I talk about the convergence of a series, I'm talking about, does the series have a sum? Does the sum of that series actually exist? Remember, when a series converges, that means the sum exists. Sometimes we can actually find the sum. Sometimes it's maybe not so easy to find the sum. But you at least know that a sum exists, which sometimes is important. So today, our order of business is we're going to go through a review of what we've talked about so far with series, and then we're going to look at three main ideas today. We're going to look at the integral test for the convergence of a series. We're going to look at a category of series that's common to encounter, call it p-series. And p-series are commonly used when you're looking at the comparison test, both the comparison test and what we call the limit comparison test. I'm going to talk about the comparison test. I'll spend the most time with the limit comparison test. That's the one that we will use in class. All right. So infinite series. And we're talking about convergence. So far, we have done basically three things. We've talked about a geometric series. So a geometric series, remember, is a series that can be written in this form. The sum as n goes from 1 to infinity of a times r to the n minus 1. And this series converges if the r value is between -1 and 1. And if it converges the sum of the series, you actually have a formula for that the sum of the series is a over 1 minus r. And then the series diverges. In other words, it doesn't have a sum if r is greater than or equal to 1 or r is less than or equal to -1. So if you can identify a geometric series, and remember, a geometric series, one way to look at this is that you have a constant raised to a power that is a function of n, right? Function of n is the exponent. And generally speaking, when you have a series that's like that, you suspect that it's going to be a geometric series. All right, we have talked about telescoping series, kind of a very narrow class of series, definitely. And a telescoping series is one where, generally speaking, you've got a general nth term that's usually a subtraction problem, and you usually have things like this. A sub n and a sub n plus 1, or it's a sub n minus a sub n plus 1, a sub n minus a sub n plus 2, etc., things like that. When you see a series where the general nth term is written in that form, or that you can write it in that form, you think about a telescoping series. And with a telescoping series, remember the idea here is to write out or expand the S sub n. And remember, S sub n is the nth term of the sequence of partial sums. Nth term of the sequence of partial sums. In other words, what happens when you add the first n terms of the series together. So you write out or expand S sub n, which is the nth term of the sequence of partial sums. And then what happens? The nth term collapses. In other words, the nth term collapses. In other words, a bunch of stuff cancels out, and you're left with a nice closed form for S sub n. And then you look at the sum of the series S to be the limit as n goes to infinity of this nth term after it's collapsed. So you expand it out, write out all the terms, and then a bunch of terms cancel, it collapses, and then you can take the limit of that nth term, what you have left, and you can usually find the sum of the series that way. We'll look at another example of a telescoping series in a little while. All right, and then finally we have the nth term test for divergence. And the nth term test for divergence is a way of showing that a series diverges. And remember, the idea here is that if you have a series in this form, right, that the nth term of the series is a sub n, and you can show that the limit as n goes to infinity of a sub n is not equal to 0. If you can show that it's not 0, then the series must diverge. The series diverges. Also, let's also right at this point and put this in a different color to emphasize this. If you show that the limit as n goes to infinity of the nth term of the series is equal to 0, you have shown nothing. This means nothing about the convergence. Because you can find lots and lots of series that diverge where the nth term goes to 0. So this means nothing right here. And I'll emphasize that over and over again every lecture and going into exam 3, I'm going to repeat that, because all the time when I test students over this material, I'm always getting students to tell me, hey, the nth term of this series goes to 0. The series converges. That's true for a sequence. It is not true for a series, right? The series, you cannot show a series converges by looking directly at the nth term like that, unless it's a geometric series, right? And so, all right. So now let's go through a little bit of a review here of the things that we've talked about. Those are the 3 things we've talked about so far. So I give you a series and I ask you, does this series converge or diverge? And really at this point, you have one of those 3 avenues of approach for the problem. You either identify it as geometric, you identify it as telescoping, or you identify that you can use the nth term test to show that it diverges. All right, so this particular series, does this series converge? I'm putting a question mark here. So now you see constants raised to n, functions of n power, and so we think geometric because of the way this is written. And so we go ahead and see if we can write it in this general form for a geometric series. So we have to use a little bit of algebra here and rules of exponents. So in the numerator, we have 2 to the 3rd power to the n. In the denominator, we have 3 to the 2nd power to the n. But you want to try to write this as a constant to the nth power. And so this would be 8 to the n in the numerator over 9 to the n in the denominator. And then finally, take the 8 to the n over the 9 to the n, and you can rewrite that as 8/9 to the n. And sure enough, this series is geometric. That is in the form for a geometric series. It's a constant raised to the nth power. So this is geometric. So I would want you to identify that when you write this out for me on a test. So you tell me it's a geometric series. Tell me what the R value is. In this case, the R value is 8/9. We know that R is between -1 and 1. 8/9 is between -1 and 1. So the series converges. That means that this particular series has a sum. And in the case of a geometric series, we can figure out what the sum is, right? The sum is S, and it's equal to A, which remember is the first term of the series, over 1 minus R. All right, and so in our problem, the first term of this series, please watch for this, that the first term in this series is when n is 1, and when n is 1, the first term is 8/9. You know, if I'd started this at n equals 0, then the first term would have been 1. So pay attention to what the first term is, right? And that's what this 8/9 is right here. That's the first term. And in this case, that's when n is equal to 1. And that's because I started this series at n equals 1. In the denominator, this would be 1 minus r, so this would be 1 minus 8/9. And so that gives us 8/9 over 1/9, or 8. And so that is the sum of this series. right? This series right here, the sum as n goes from 1 to infinity of 2 to the 3n over 3 to the 2n is exactly equal to 8. Not approximately equal to 8, it is exactly equal to 8. Because what we just showed was that the more terms you add up in this series, and remember, the series has an infinite number of terms, but the more terms you add up in this series, the closer the sum will get to 8, and you can get arbitrarily close to 8 by taking more and more terms. You tell me you want to get within 0.0001 of 8 with the sum, and we can add up enough terms that we get that close to 8. You know, and no matter how close you tell me to get to 8, I can always add up enough terms to make the sum that close to the number 8. Okay? So here's an example of a convergent geometric series. All right, the next problem. Now this looks kind of different, but this is actually another example of a geometric series. And there are some problems in the textbook like this. It says show that 0.9 with a bar over it, and remember with 0.9 with a bar over it is really 0.9999, etc., right? An infinite string of nines for this decimal. Show that this is identically equal to the number 1. All right, now so we're saying that 0.9 with a bar, 0.9 repeating, is equal to exactly 1. Notice I am not saying that it's close to 1. I am saying that 0.9 with a bar in it, over it and 1 are actually the exact same number. It seems crazy to say that, but that is absolutely a true statement. Excuse me. So what you have here, is you have 0.9 with a bar over it, these repeating nines like this, is really 0.9 plus 0.09 plus 0.009 plus 0.0009, etc. In other words, you can take a repeating decimal like this and you can write it as an infinite series. Now, if you take each of these decimals and write them as fractions, I think it's easier to see. So you have 9 tenths plus 9 hundredths plus 9 thousandths plus 9 ten thousandths plus etc., etc., right? And so that would be 9 over 10 to the first plus 9 over 10 to the second plus 9 over 10 to the third plus 9 over 10 to the fourth. And so you see, you can start seeing that this is going to be actually an example of a geometric series. This is actually the sum as n goes from 1 to infinity of 9 times 1 over a power of 10, 1 over 10 to the nth power. Right? That every term fits exactly that form. And so, in fact, this is a geometric series. If you want to, you could write this as n equals, the sum is n equals 1, the sum as n goes from 1 to infinity of 9 times 1/10 to the nth power, like that. And so this is geometric, and the r value is 1/10. And r is between -1 and 1, so the series converges. So in other words, this series has a sum. And what is the sum? We have our little formula. It's a over 1 minus r. Remember that a is the first term of this series. So that's when n is 1. And so the first term of this series is 9 tenths. And in the denominator, this is 1 minus r. So this is 1 minus 1/10. Right? And so notice what you get here. You get 9 tenths over 9 tenths. And that is exactly equal to 1. And so sure enough, it is absolutely true that 0.9 with a bar over it is equal to 1. It's a crazy idea, but that is absolutely true. By the way, there's other ways to prove this. If you think that I'm kidding you or I'm pulling the wool over your eyes on this, this is absolutely not the case. This is absolutely true. Another way to prove this, by the way, another really simple way to prove this is simply to take 1/3 and write it as 0.3 repeating, which we all know is true. And so what do you have here? If you take that number 3 times, like this, and add those, so what happens on the left side, 1/3 plus 1/3 plus 1/3 is equal to 1. But on the right side, what have you got? 0.3 repeating, 0.3 repeating, 0.3 repeating. When you add those together, what do you get? In every column, you get a 9. You get 0.9 repeating. And sure enough, what do we get? That 1 and 0.9 have to be exactly the same number. And so that's absolutely true. Okay, so that's maybe a little bit of a surprising result, but it's definitely a true statement that we could prove using infinite series. All right, another way of looking at geometric series, by the way, that we did not really talk about last time, was we could take a series of variables like this one right here. Notice that this is the sum as n goes from 1 to infinity of x minus 1 to the n. And, think about what happens here. If you refer to this as a function, I say that I have a function that's defined as this infinite series, notice for every x value, so let's say we get f of 3, you get an infinite series. When x is 3, what do you get? You get 2 to the n. Now notice what you get, though, for f of 3 is you get a geometric series that diverges, right? This is geometric, but the r value is 2, so this diverges. And so that means that in this case, f of 3 does not exist, or another way to say that is that 3 is not in the domain of this function. Because when you tried to plug in 3, you got a divergent series. On the other hand, if you look at f of 3 halves, right, that would be the sum as n goes from 1 to infinity of 3 halves minus 1 to the n. And that would be the sum as n goes from 1 to infinity of 1/2 to the n. And what do you get there? You get geometric also, but big difference here, r is 1/2. This converges. And so 3 halves is in the domain of this function, right? Because we get a convergent series. So 3 halves is in the domain of f, since f of 3 halves gives a convergent series. Okay, so our question then in this problem is, so this is our question now. For what x values does this series converge? And when you answer this question, you are actually finding the domain of this function f, this crazy function that's defined as an infinite series. Now, this is a prelude to some of the most important work we'll do in this chapter, or in this unit at the very end. Okay, so this is kind of a foreshadow of things we're going to be covering. Well, this series could be looked upon as geometric at the beginning, where r is x minus 1. Okay, so in our series, you've got something raised to the nth power. That thing, if it's a constant, right, then this is going to be geometric. And for any x value, I would get a constant there. So it's geometric. R is x minus 1. And what do we know? That we know that a geometric series converges if r is between -1 and 1. So what is r in this case? R is going to be x minus 1. And we get a nice little inequality that we can solve. Add 1 and we get 0 less than x, which is less than 2. We know that for all x values between 0 and 2, we get a convergent series from this function. So for these x values, for any x value between 0 and 2, the sum as n goes from 1 to infinity of x minus 1 to the n converges. And any x value outside that interval, it's going to diverge. Now, one thing that is not exactly, that we've got to look at a little bit more carefully, and we will do this later in the semester, is the endpoints of the interval. Sometimes you get a convergent series, sometimes you get a divergent series. So these endpoints we'll have to look at more carefully later. But for now, we know that all the x values between 0 and 2 for sure make this series a convergent series. And so that's the domain of this function f. That's it. We've actually found the domain of the function. Right there. That's all the x values between 0 and 2. All right. That little interval we found sometimes is called the interval of convergence. Because all those x values in that interval give you a convergent series. So this interval from 0 to 2, we sometimes will call the interval of convergence. All right, now let's look at another example like that. Okay, so let's say we have this series. The sum as n goes from 1 to infinity of x plus 3 over 4 to the nth power. Okay, so this series we could look at, this is a series of variable terms, but we could look at this as geometric where r is x plus 3 over 4. Because that's the thing that's being raised to the nth power. And so what do we know here? That this series would converge if x plus 3 over 4 is between -1 and 1. And so then just solve that inequality for x, So multiply through by 4. So you get -4 less than x plus 3, which is less than 4. And then subtract 3, and you get -7 less than x, which is less than 1. And so that would be our interval of convergence here for this particular series. That we know that for all x values, if you pick any x value in that interval from -7 to 1, you are going to get a convergent geometric series. Any x values on the outside of the interval, you're going to get a divergent geometric series. Now, the only thing we don't know for sure is what's going on at -7 and at 1 themselves. We'll talk about those, like I said, later in the semester, or later in this unit on sequences and series. So, but we know for sure that any x value between -7 and 1 would make this a convergent series for sure. Okay, so that would be our interval of convergence. All right, let's look at one last problem like that. I've worked, this will be 3 of these that I'll work. And I will ask a question like this likely on your next exam, on exam 3. Or on the final exam. All right, we have the sum as n goes from 0 to infinity of 5 times x minus 2 over 3 raised to the nth power. So now be careful in this problem. The 5 is a constant factor and is not part of the r value. Right? R is just the expression that's being raised to the nth power. That's our common ratio. And so r in this case would be x minus 2 over 3. And so this series would converges if that r value is between -1 and 1. So x minus 2 over 3 has got to be between -1 and 1. So you multiply by 3, you get -3 less than x minus 2, which is less than 3. add 2, and you get negative 1 less than x, which is less than 5. And for all of those x values, then you will get a convergent geometric series. Notice the constant 5 really didn't affect this in any way whatsoever. It's the r value that controls whether the series converges or not. And so this would be our interval of convergence, this interval right here, or the domain of the function, remember. Right? You take any x value out of that interval, and you're going to get a convergent geometric series, guaranteed. All right, so, and if you have a question about that, if you're worried about that, pick an x value in that interval. Pick any x value you want in that interval. So I'll pick x equals 3. 3 is between negative 1 and 5. So I'm looking at f of 3 in this series. Notice this series starts at 0. And you'd have 5 times x is 3, so this would be 3 minus 2 over 3 to the nth power. And this would be the sum as n goes from 0 to infinity of 5 times 1/3 to the nth. Definitely convergent geometric series. R is 1/3. So this definitely converges like we expected it would. And the sum of this particular series would be a over 1 minus r. Now be careful, this series starts at 0, so a is 5 in this problem over 1 minus 1/3. Got to be careful, this series started at 0, right? And since it starts at 0, the first term of the series is when n is 0, and you'd have 5 times 1/3 to the 0. So you have 5 over 1 minus 1/3. This is 5 over 2/3, or 15 halves. And so if our function is defined to be this infinite series, whoops, wrong series, sorry. I was copying the first one down. Let's start that again. So this would be n is 0 from 0 to infinity. And you have 5 times x minus 2 over 3 to the nth. So that's our function. Then what we just showed was that f of 3 is actually equal to 15 halves for this particular function. That when x is 3, you've got an infinite series that converged to 15 halves. So that's our 15 halves would be our range value. All right, so we've gone through some problems with geometric series. Kind of go back over that again. So now let's go over some things about the nth term test. So if you have this series, the sum as n goes from 1 to infinity of 2 minus 1 over 3 to the n, right? If you look at the nth term of that series, the nth term is 2 minus 1 over 3 to the n, and you look at the limit as n goes to infinity of the nth term, so that's the limit as n goes to infinity of 2 minus 1 over 3 to the n. Well, that second term, right, that is 1 over infinity, right? That goes to 0. And so notice this limit is 2. And so this is not equal to 0. And so our conclusion at the end on a problem like this we would say that by the nth term test, this series diverges. It does not have a sum. All right, and because remember the nth term has to go to 0. All right, so think about the function that you've, or the sum that you've got, and think about whether it might be a candidate for the nth term test. All right, this is the next series right here. The sum as n goes from 1 to infinity of 3 to the n over n cubed. Now, you've got 3 possibilities. It's geometric. Well, it's not geometric because of the n cubed. Certainly not telescoping, because I don't have like an n plus 1 and an n, or an n plus 2 and an n in this expression. I don't have 2 terms in this expression. So for all sorts of reasons, it's not telescoping. So that means the nth term test is the likely culprit here, right? That's our likely way of proving whether this series converges or diverges. And so what we need to do is show that the limit as n goes to infinity of 3 to the n over n cubed is not equal to 0, right? We need to show that. All right, so technically what you're doing here is you're using this function f of x equals 3 to the x over x cubed, and you're looking at the limit as x goes to infinity of 3 to the x over x cubed, which is infinity over infinity. And we can use L'Hopital's rule here, right? So using L'Hopital's rule, we have that this is the limit as x goes to infinity of 3 to the x times the natural log of 3 over 3x squared, right? Which is infinity over infinity, again, unfortunately. So we use L'Hopital's rule again. In the numerator there, the natural log of 3 is just a constant. It comes along for the ride, and every time you take the derivative of 3 to the x, you just get 3 to the x times the natural log of 3. So you get an extra natural log of 3 every time you take the derivative. And so that would be over 6x right there. Still infinity over infinity. And then you finally take the limit as x goes to infinity. You take the derivative one more time using L'Hopital's rule. The natural log of 3 to the second power is still just the natural log of 3, or is a constant. And so you're just taking the derivative of 3 to the x. So you just get another natural log of 3 as a factor in there. You get 3 to the x natural log of 3 cubed. And then this would be over 6. And finally, that is not infinity over infinity. That's infinity over 6, which is infinity. And so what do we know here? We know that we just showed that the limit as n goes to infinity of the nth term here is not equal to 0. So by the nth term test, and I want you to say that, write that out, by the nth term test, this series diverges. I will penalize you if you do not mention the nth term test when you do a problem like this. All right, and that you're showing that the nth term does not go to 0. All right, and I know I'm taking some time up here in this lecture, but I really wanted to go back over everything again. So let's look at a telescoping series. Right, so our example here would be the sum as n goes from 1 to infinity of 1 over n minus 1 over n plus 2. Right, a very typical example of a series that would fit this mold of being a telescoping series. So we look at the nth term of the sequence of partial sums. Nth term of the sequence of partial sums. We call that S sub n. In other words, we are adding the first n terms together. So S sub n would be, when n is 1, you'd have 1 minus 1/3. And that's when n is 1. Plus, when n is 2, you have 1/2 minus 1/4. Plus, when n is 3, you have 1/3 minus 1/5. And you start to see how things are going to cancel out. I'm going to go out to n equals 4 at the beginning here to make sure that you're really clear on how this is going to work. So you have 1/4 minus 1/6 plus dot, 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 plus. And I'm going to write the last 3 terms out. So the n minus second term, the n minus first term, so the n minus second term, the n minus first term, and finally the nth term at the very end. So the n minus first term, every place you see an n, just put n minus 2. So this is 1 over n minus 2 minus 1 over n. n minus first term. Every place you see an n, put n minus 1. So you have 1 over n minus 1 minus 1 over n plus 1. And then finally, the nth term would just be 1 over n minus 1 over n plus 2. Now look at how things, okay, so you've expanded. And then what happens? This is going to collapse. The 1/3s cancel out. The 1/4ths cancel out. The 1/5ths, the 1/6ths, those are all going to go away. They're going to all have matches somewhere. And so notice at the beginning here, the terms that survive are 1 and 1/2. And then at the very end, you have n plus 2 does not have a match. But 1 over n, that has a match. 1 over n plus 1 does not have a match, but 1 over n minus 1 is going to have a match later on in one of the terms in the n minus third term. And so there are two terms that survive at the end also, 1 over n plus 1 and 1 over n plus 2. And so the nth term of the sequence of partial sums collapses to 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. You end up with 4 terms at the end on that one. And the limit, as n goes to infinity, you now take the limit of the nth term here. And what do you get? The 1 over n plus 1 and the 1 over n minus 2 will go to 0 when you take this limit. Right? Because those will both be 1 over infinity. Or that would be the form you get. So those go away. Those are going to go to 0 when you take this limit. And you're going to end up with 3/2. And that is the sum of the series. So the series converges, and it converges to 3/2. Very unusual type of series, but it gives you an illustration of what can happen when you expand out the nth term of the sequence of partial sums. All right, so that gives us a good overview of the 3 things we've talked about. Now we're going to move on and add to our list of things we can do to show that a series converges. So the next test we are going to use is called the integral test. And like the name suggests, it involves an integral. All right, and so we are looking at this series. The sum as n goes from 1 to infinity of a sub n. All right, so first, there's a bunch of things that have to be true in order to use the integral test. First of all, f of x has got to be equal to f of n for all values of n. Right, so f of x and f of n. So you remember n is some counting number, right? So for all those counting numbers, those have got to be equal. F of x has got to be decreasing. All right, and the way you show that f of x is decreasing is you just show that f prime is negative. F of x must be positive. So f of x has got to be greater than 0 for x greater than 1. And actually, technically, for x greater than some number, some real number. 1 is the most common one to use. And f of x must be continuous. In other words, no discontinuities for x greater than 1. All right, so basically the integral test goes like this, that if you've got all these things are true, so in particular, if f of x and a sub n are the same thing for these n values, then you've got that the improper integral of f from 1 to infinity and the series where the nth term agrees with our function either both converge or both diverge. In other words, our series does the same thing as the integral. And interestingly, they not necessarily to the same number, right? So just because the integral converges to something doesn't mean the series converges to the same thing. So not necessarily to the same number, interestingly. So all this is a device to allow us to prove that a series converges, not necessarily to what it converges to. So not necessarily to the same number. There's actually a way to narrow down an error involved in what the series converges to. So you can actually make some approximations. We are not going to go through those error tests. We are just going to be going through the convergence tests in particular. All right, so let's look at some examples of the integral test. The integral test, you have the sum as n goes from 1 to infinity of 1 over n squared. All right, so if you're going to use the integral test here, what do you need to do? You form a function first. So f of x is going to be 1 over x squared. That's easy. You just take the n's and replace them with x's. And then you've got to show all those different things at the top, that the function's positive, it's decreasing, continuous. Well, it certainly fits all those conditions, doesn't it? Because certainly f of x is positive, is greater than or equal to 0. It's just greater than 0 for all x greater than 1. No question about that. The only discontinuity is at 0. So for x greater than or what equal to 1, for x greater than 1, always continuous. And then finally, is it decreasing? So you look at f prime of x, and f prime of x is negative 2 over x cubed. It's just the power rule because it's x to the negative 2. And that is negative. What do you have? That f prime of x is less than 0 for all x greater than or equal to 1. And so what does that mean? That the function is decreasing. F is decreasing. And so what have we done? We have actually talked about everything that the theorem lays out, right? We know that the function is positive. The series is positive. We talked about the discontinuities. So x is greater than 1. It's always continuous. And finally, we have that f is decreasing. Those are the big three that you got to look at when you're talking about the integral test. So we can use the integral test in this problem. So the integral test, we look at this improper integral. The integral from 1 to infinity of 1 over x squared dx. And remember how you do an improper integral, or how you evaluate an improper integral. You rewrite this as a limit. The limit is a goes to infinity of the integral from 1 to a of 1 over x squared dx. And then you evaluate that integral, see whether it exists or not. And so you've got, let's see, the antiderivative for 1 over x squared is going to be negative 1 over x, right? And so you get negative 1 over x. Whoops, got to write the limit still. Back up there. So this is the limit as a goes to infinity of negative 1 over x evaluated from 1 to a, like that. And so that would be the limit as a goes to infinity of negative 1 over a plus 1. And sure enough, that is equal to 1. And so the integral converges, and this is what I'd want you to write at the end. The integral converges to 1. The integral converges to 1. So then you would finish by saying by the integral test, the series converges. You can't say it converges to 1. You can just say that it converges. There's a process where you can go through and narrow down what it does converge to, but again, we are not going to go through that aspect of these kinds of problems. We're just going to show that these things actually converge or diverge. All right, let's look at another example of the integral test. So our next example is the sum as n goes from 1 to infinity of 1 over n. This should look familiar to you. This is something we mentioned last time. This is a famous series. This is an important series. This is called the harmonic series. And if you remember last time, we simply made the statement that this series diverged, but we didn't prove it. Well, now using the integral test, we can actually show that this series diverges. So we form the function f of x equals 1 over x. This function is certainly continuous and positive for x greater than or equal to 1. And f prime of x is negative 1 over x squared. And so that tells us that f prime is negative for x greater than or equal to 1. And so f is decreasing. We needed that also in order to use the integral test. And so what do? We are ready to use the integral test. So we write down the improper integral from 1 to infinity of 1 over x dx. And so that would be the limit as a goes to infinity of the integral from 1 to a of 1 over x dx. That's an easy antiderivative. So the limit as a goes to infinity of the natural log of x from 1 to a. And so that would give you the limit as a goes to infinity of the natural log of a minus the natural log of 1. Now the natural log of 1 is 0. And the natural log of a, as a gets large, that goes to infinity. And so what do we know here? That the integral diverges. So by the integral test, the series diverges also. And so what have we just proved? We've just proved that the harmonic series diverges. It does not have a sum. And remember, this is the harmonic series. This is definitely an important series. Right? That thing diverges. No sum associated with that series. Okay, let's see. Let's go on and talk about, I want to make sure that I have time for everything I need to talk about today and that we don't go too late also. So the next thing we want to do is talk about what are called p-series. So we've talked about the integral test. If we have time, we'll look at more examples, and I'll probably end up looking at an integral test example next time. A p-series is a series that fits this form. The sum as n goes from 1 to infinity of 1 over n to the p, like that. And p has to be greater than 0. This is an example of a p-series. So, for example, if you have this series, a 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, right? This is an example of a p-series, right? Because notice that the denominators are all squares, right? And it's just counting to determine what each square is. This is the sum as n goes from 1 to infinity of 1 over n squared. Right? The denominator would be 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. And so that would be an example of a p-series. All right, if you have 1 plus, and by the way, what's p equal to here? P would be equal to 2. 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4, right? That would be an example of a p-series. And this would be the sum as n goes from 1 to infinity of 1 over the square root of n, or 1 over n to the 1/2 power. P would be equal to 1/2 for this particular series. All right, what we can do is we can, and we're not going to take the time to do this right now only because of the interest of time, but you can use, and it's really not too hard to do, but it does take a little bit of time. We can use the integral test to show the following about a p-series. Right? If you have a p-series, if p is greater than 1, the series converges. And if p is between 0, remember p has to be greater than 0, and 1, including 1, then the series diverges. All right, a p-series is an important class of series. This is the general shape of a p-series right here, and this is the conclusion from the integral test, is that if p is greater than 1, the series converges. If p is between 0 and 1, the series diverges. So it ends up being, if you have a p-series, it's super easy to tell me whether it converges or diverges. And I'm going to let you use this result to do that. So if we have the sum as n goes from 1 to infinity of 1 over n to the 4th, right? Let's say I gave you this problem on a test. Then what would you do? You would tell me that this is a p-series because of the shape of the series, because of the shape of the nth term, and that p is equal to 4, and that p is greater than 1. And then you just simply tell me that the series converges. This is absolutely the easiest type of series we can encounter, pretty much. And in other words, this sum exists. Now you have to go through a little bit more heartache to get some kind of an approximation on the sum, and that's not what we're talking about right now. We are just simply talking about whether the sum actually exists or not. The next example, the sum as n goes from 1 to infinity of 1 over the square root of n. Right? That's the same as the sum as n goes from 1 to infinity of 1 over n to the 1/2 power. And so this is a p-series. Remember, I will want you to tell me it's a p-series with p equal to 1/2. P is less than 1, and so this series diverges. All right, so these p-series are super easy, and if you combine them with the comparison tests that we're about to do, then it makes it even more powerful to be able to identify these p-series like this. With the comparison tests, first test you have is what we call just the comparison test. This one I'm not going to hold you responsible for on the exam. It's called the comparison test. The limit comparison test, which is a little bit more precise version of this test, is one that I am going to hold you kind of responsible for. With the comparison test, basically you've got this idea that if you have a sum of a sub n's, and this converges. So we'll say that this sum of the a sub n's converges. And b sub n is less than or equal to a sub n for all n greater than or equal to 1. And technically it doesn't have to be 1, by the way. It can just be any constant there. But if the b sub n's are always less than the a sub n's and the a sub n's converge, then the b sub n's converge also. So in other words, if you can take a series and actually trap it underneath the convergent series, it has to converge also. When I say trap it underneath, it means it's less than, right? So if you're less than a convergent series, you have to converge, basically, right? If you are less than, and this is extremely informal, but if you are less than a convergent series, you must also converge. In words, that's kind of, and very informally, that's what the first part of the comparison test says. And the second part goes like this. If the sum as n goes from 1 to infinity of a sub n's diverges, and the b sub n's are always greater than or equal to the a sub n's for all n greater than or equal to 1, then the b sub n's diverge. So, in very informally, if you are greater than, and when I say greater, I don't mean like better. I'm saying greater like in, right, bigger, it's bigger numbers. But if you are greater than a divergent series, you must also diverge. All right, so you can use this test to frequently to prove that a series that looks like a convergent or a divergent series also converges or diverges. But that's all I'm going to state with the comparison test. And what I'm going to look at more carefully and to finish class up today is the limit comparison test. And the limit comparison test is our sixth item in our list of series things, right? We've got, so what do we have? We have geometric, we have telescoping, we have the nth term test for divergence, we have the integral test, we have p-series, and now we have the limit comparison test. So the limit comparison test goes like this. If you have two series, the sum as n goes from 1 to infinity of a sub n, and the sum as n goes from 1 to infinity of b sub n, if the limit as n goes to infinity of a sub n over b sub n, that's the comparison there. You're actually comparing terms. You're looking at the ratio of corresponding terms. If that limit is L, if you get a constant, and L is positive and L is finite, in other words, not infinity, then either both series converge or both diverge. And from a practical standpoint, what this means then is that if you can compare a series that you're given to a known series, a series that you know converges or diverges, then you frequently can prove an unknown series converges or diverges also. Now, a follow-up to the limit comparison test goes like this. If the limit as n goes to infinity of a sub n over b sub n is equal to 0, and the sum as n goes from 1 to infinity of b sub n converges. Now think about it, that fraction is going to 0. The a sub n over b sub n is 0. So that means that the numerator has to be smaller than the denominator, right? And so if the b sub n's converge, then the a sub n's have to converge also. Because if you think about it, that fraction, you're comparing the two series, and you're essentially saying what we talked about on the comparison tests on the previous screen, that you've got to be a series that's less than a convergent series, and so you have to converge also. And if the limit as n goes to infinity of a sub n over b sub n is equal to infinity, and the sum as n goes from 1 to infinity of b sub n diverges, then the a sub n's diverge also. And if, again, when you compare a numerator and a denominator and you get infinity as the answer, that means that the numerator has to be bigger than the denominator. And if the numerator is bigger than the denominator and the denominator diverges, right, what does that mean? You're bigger than a divergent series, so you have to diverge also. So it's just a way of really stating what we just said on the previous screen about using the comparison test. All right, so from a practical standpoint, the limit comparison test, the big question is, what series do you use as a comparison series? Sometimes that can be super, super easy, and sometimes that maybe not so super, super easy. So here's a series right here. The sum as n goes from 1 to infinity of n squared plus 1 over n to the 5th plus 1. When you have a rational expression like this, right, this is a rational expression, polynomial over a polynomial, simply look at the difference in the degrees. So look at the difference in the degrees between the numerator and the denominator, which in this problem, that would be 3. The difference in the degrees would be 3, because it's n squared over n to the 5th. It's a second degree polynomial over a 5th degree polynomial. So what that means is you compare to the sum as n goes from 1 to infinity of 1 over n cubed. So that's what we're going to do here. So we're going to use limit comparison. We're going to compare to the series 1 over n cubed. 1 over n cubed is a convergent p series because p is 3 there. All right, so we look at the limit comparison test. By the way, it does not matter which series you put in the numerator and which series you put in the denominator. It does not matter. You will get the same conclusion. You can make the same conclusion either way you write it. So if I write n squared plus 1 over n to the 5th plus 1 over 1 over n cubed, all right, so let's write that kind of invert and multiply there, right? And what do we get? We get n to the 5th plus n cubed over n to the 5th plus 1, right? Remember, you're multiplying the outside 2 and multiplying the inside 2. You're inverting and multiplying, basically. And what do you get there? That limit, because they're both 5th degree polynomials, that limit is 1. And so by limit comparison, both series diverge. That'd be nice. Both series converge. There you go. Sorry about that. Both series converge. 1 over n cubed converges. We got a constant for the limit here, right? We got a finite number, 1, as the comparison. When we took the limit, we compared corresponding terms. And so both series have to do the same thing, and so this one has to converge. All right, let's look at another example. So there's an example. Next example. The sum as n goes from 1 to infinity of 3n plus 1 over 5n plus 3. Now I slipped this one in here on purpose because I don't want you getting too narrowly focused on one test here. Don't forget things like the nth term test. And look at, if I take the limit of the nth term of this series, right, I get 3/5. You don't have to use limit comparison here. You just say by the nth term test. This series diverges, right? Because you didn't get 0, right? You got to get 0 there, and if you don't get 0, you know you know that the series diverges. All right, so don't overlook things like that. All right, let's look at 2 series here, kind of side by side. Let's look at the sum as n goes from 1 to infinity of n squared over n to the 4th plus 1. And right alongside that, let's look at the sum as n goes from 1 to infinity of n cubed over n to the 4th plus 1. Right, and so what do? We look at the difference in the degrees here. And so in the first series, we compare to the sum as n goes from 1 to infinity of 1 over n squared. On the second series, the difference in the degrees is 1, so we compare to the sum as n goes from 1 to infinity of 1 over n. Don't get sloppy about how you write this stuff out. Make sure you write these series out correctly and write out the steps here. Tell me what you're comparing the series to. The first one is a convergent p-series, right? P is 2. The second one is the harmonic series that we're comparing to, and we know that diverges. All right, so, and then write out these steps. Don't take shortcuts here. Write out your steps. So this is the sum as n goes from 1 to infinity of n squared over n to the 4th plus 1 over 1 over n squared. And so that would be the limit as n goes to infinity of n to the 4th over n to the 4th plus 1. That limit is 1. And so we would finish by saying, don't just stop with 1, certainly. Don't just stop with converge. What do you got to say? You got to say by limit comparison test. Both series converge. All right. On the second one, when we look at this limit, we have the limit as n goes to infinity of n cubed over n to the 4th plus 1 over 1 over n. So this is the limit as n goes to infinity of n to the 4th over n to the 4th plus 1. That limit is 1. And so here you've got by limit comparison. Both series diverge. Right, so with a rational expression, just looking at the difference in the degrees will get you what you need to compare to. Now, getting that comparison series is not always an easy thing to do. So look at this example right here. This is actually a problem out of your book. This is number 208 in section 5.4. you have the sum as n goes from 1 to infinity of the natural log of n over n to the 0.6, and that's all squared. And so that's the question here is, does this converge or diverge? This is not a simple expression. It's not a rational expression. It's not necessarily obvious at all what to compare this to. And so what you can do is you can pick a comparison series and use trial and error here and see if what you get would work out. And if it doesn't, then you try something else, right? So for example, what you could do is, and I'm not going to work through all of this part of it, but you could compare to the sum as n goes from 1 to infinity of 1 over the n to the 1.2, like that, which is a convergent p-series because p is 1.2 there. Unfortunately, this does no good. You will get a result that is inconclusive. And so that is not the appropriate series to compare to. But on the other hand, if you compare to this series, 1 over n to the 1.1, not 1.2, but 1.1, which is also, by the way, a convergent p-series. Right, so compared to that series, which is a convergent p-series, you will actually get a result in this case. But it is not a trivial problem to get the answer here to actually show that both series are going to converge here. 1 over n to the 1.1 is a convergent p-series. So if you can compare the two series and you get a constant as an answer, then you're good. Or depending on how you compare the two series, and let's actually write out the comparison here. If you take the limit as n goes to infinity of 1 over n to the 1.1, notice I'm using the comparison series in the numerator here, over the natural log of n squared over n to the 1.2, what you will find here is that this answer is, and so notice, by the way, this is the convergent p-series here in the top, and this is our unknown series here. And so what do I want to get as an answer? I either want to get, if I want to get a result here, I either want to get a constant or I want to get infinity as the answer. If I get infinity as the answer, the only way you can get infinity is if the numerator is bigger than the denominator. And remember, if you've got a convergent series and you're less than a convergent series, then you've got to converge also. So we want here either a constant or infinity. And so what I'm going to do is I'm going to leave this for you. I'm going to tell you what the result is, though. And the result is, and you have to use L'Hopital's rule to deal with the limit in between, ... you end up with infinity as the answer when you look at that limit. But like I said, you're going to have to do some work to show that. And if you can show that, then what has to be true here is, and what I'm going to say is, so you, I'm going to put quotes around that, so you, the unknown series, are less than a convergent series. So you must converge also. That's tricky at the end, and the tricky part is those ... dots right there. There's a lot of steps in between there to show that you actually get infinity there, and so that's something I want you to definitely see if you can do that. All right, and so we have now finished up through section 5.4 in your textbook. And so remember, what I am going to do is I'm going to give you a list of series. I'm going to send you a list of series tomorrow, and I'm going to pick from those problems that I'm going to want you to turn in. So look for a homework assignment to be sent tomorrow. And then I'm going to pick from those problems and ask you to turn a couple of those in, 2 or 3 of those. I'm going to ask you to turn those in on Sunday evening for your next homework assignment. All right, so that gives you definitely something to work on. Also, remember that exam 2 review will go up by Thursday of this week. So everyone, please work on some of these series problems, especially that sheet that I'm about to send you tomorrow, and get some practice in. Don't hesitate to ask me questions if you have questions. I'll be happy to help you with those.